Before we start the presentation, Nicholas and I both are from the San Francisco office working on the safety organization, which prioritize user safety when using our platform. Recently, we launched a very exciting new service called RideCheck, which detects suspicious trip activities. For example, when a user is on an anomaly long stop or a potential car accident, the app will send a RideCheck message to the users and simultaneously forward this information to our safety response team, which would later follow up with a phone call to provide any assistance that's needed. So here is the in-app experience. First, we'll send in a check-in message to verify that a crash actually happened on the trip, and later we'll provide emergency call lines for them to reach out to either the police or our proactive response team.
So what will we be going over today? First, we'll introduce a model, our first iteration, how we detect a crash on an Uber trip. Second, we'll explain why we chose Flink and how we integrated Flink into Uber's internal infrastructure. Then we'll walk you through 3 iterations of Uber's Flink crash detection pipeline. First, a modular, very light topology operating only once a trip ends, meant to be light enough, avoid resource intensiveness, and just prove out the concept. Our second iteration was then something of a refactor. We rebuilt on a reusable sensor platform that served not just our need, but other needs within Uber. And finally, our third iteration finally approached a real-time solution. We started on-trip crash detection, even though it meant sacrificing certain model features.
So how does our first model look like? So this is how a trip looks like to Uber for a business perspective. This is a GPS data visualization of a trip. First, the car starts out rather smoothly and stops in the middle of the trip. Later, the rider cancels the trip. So there are various reasons for a car to stop in the middle of their trip. It could be due to they're passing through a relatively busy traffic, or they encounter a roadblock event for some festivity reasons. So from a business perspective, we could infer where the rider is being dropped out and comparing that to where he or she intended to be dropped off. And also we could check out the status of the trip, for example, if it's canceled or does it end normally. And lastly, we also have a location context of where the car is in terms of whether or not they're in a busy street or in a movie theater or in some compacted area.
And so in addition to all of those really valuable trip context features, we also have a lot of sensor data that tells us very important information about a trip. First, we have GPS data, which gives us a speed profile over the course of the trip. Over this particular trip, there was a brief stop at the beginning, maybe a traffic light. We reached a high speed along maybe that green highway, and then ultimately came to a long stop for many minutes. And in addition to this data source, we have accelerometer data. The accelerometer is the sensor on your phone that tells you what forces it's experiencing. For example, whenever you change the orientation of your phone, that's your phone sensing the force of gravity and adjusting accordingly. And so on this particular trip, there was a force of greater than 3 Gs, greater than 3 times the force of gravity. And that's actually a very valuable signal that a crash has occurred. And from these 2 sensor streams, we're able to engineer sensor events. In the case of GPS speeds, we engineer long stops. And in the case of accelerometer readings, we engineer force spikes.
All right. So this model is actually built on a huge historical data from Uber with Spark. And Uber has relatively an advantage here because whenever a car accident happens, there will be a rather detailed information on the intensity of the crash and also the location of the crash. So together we have some really good label for model training. And this model is actually trained and hosted on our machine learning platform, Michelangelo. Now, let's move on to choosing and integrating with Flink. So for our service, it is really easy for us to say that we choose Flink because at that time when we were migrating to a streaming service, Uber also migrated from Samza to Flink. And the reason that Uber chooses Flink over Samza is for its rich APIs such as key by, join, and window functions that really reduce the duplicate engineering effort, and also its promise to support batch processing and exactly once guarantee really helps with the ease the backfilling effort to not having to rewrite the streaming logic in batch mode, and the exactly once guarantee would satisfy a lot of the services that that is related to finances. This is an example of how Uber's infrastructure integrate with Flink. So on the bottom right corner, you could see that when we're reading in an input stream, we use our Kafka topic name to grab a source function that translates Kafka topics into Java objects. And this is all made possible because we have a centralized schema registry that stores Avro schema and have the definition according to the versions. So in our configuration files, we only need to specify the Kafka topic name and also the version, and then we could get this source function that reads in our input data stream.
In addition to integrating with Kafka, we also had to do a bit of work integrating with the metrics infrastructure at Uber. Uber has an in-house open source metric system called M3, which has a lot of similarities to Prometheus. And so it made sense to implement our own custom metric reporter, lightly adapting Flink's Prometheus reporter. We actually report directly to Prometheus, and then there's a Prometheus scraper that ingests into the Uber metrics ecosystem.
All right, so our first iteration of the model really utilized all the sensor data from different sources within Uber, and then consolidate on a post-trip level to analyze whether a car crash has happened on a specific trip. And this is also the first time that our team firsthand was dealing with the sensor data at Uber. So the scale of the data at Uber is around terabytes per day. Uber operates tens of millions of trips daily, and each sensor payload is about megabytes sized. So in addition to that, different sensor also comes at different frequency and different sizes. For example, GPS points are uploaded point by point in a seconds increment, whereas accelerometer readings are uploaded in minutes batch payload with minutes intervals. So joining sensor data is extremely difficult as we're all here at Flink and talking about all the problems with the trade-off between state size and data coverage. So in our first iteration, we really focus on reducing the streams joins as much as possible. So we are utilizing the unique characteristic of a car crash event in that it is very rare, and there are some features that's really crucial to a collision. For example, a spike in accelerometer reading followed by a stop to the GPS location. So by detecting stop and spikes from our GPS sensor reading and accelerometer readings, we're successfully able to condense terabytes of data into gigabytes of data streams. And after we condense these data streams, aggregation by our trip business context and joining of the GPS sensor payload and accelerometer becomes a lot easier. So this is a lightweight modular topology of our first iteration detection. You could see that there are a lot of jobs, and then the reason for these many jobs is for resource isolation and debuggability, which are obvious. And more importantly, we were hoping that with all these features that we extracted intended to feed our machine learning model, we could reuse these features with other teams who are also doing similar efforts within Uber.
And so let's take a quick look at a particular job, the job joining between trip stops and trip spikes. And we see how easy Flink makes joins compared to, say, something like Samza. We're able to use a session window after first deduplicating the two streams. We expect just 2 messages per session because of the deduplication. And so we're always just waiting for the configured gap. We'll receive a message A, and we'll wait up to that configured gap for message B to come in. And we see the real power of windows in Flink. We trigger the very moment that both messages have arrived, and we immediately free the state.
Okay, so the second iteration of our pipeline evolution is built on top of a reusable sensor platform. And this change is brought on because of a major infrastructure change, which leads to a huge simplification on our pipeline architecture design and also enables us to deploy a more complicated deep learning model in the pipeline. So why do we need this infrastructure level change? Just for the previous reason that I mentioned, our previous iteration was intentionally to be very modular so that we could share some sensor features with other teams. And take an example from our RideCheck service, other trip anomaly detection, long stop detection. Supposedly, the stop feature that feeds into our crash detection and this long stop detection that a trip abnormally needs, they should be quite similar. However, due to our products have very different criteria for data latency, data quality, data precision, and more importantly, also we have different definitions of stops. Because of these reasons, it makes more sense for us to develop our own feature than to share one. Furthermore, there are so many other sensor aggregation efforts that happen within Uber. So what we're doing to congregate sensor data based on certain business criteria is not unique within Uber. For example, fraud detection and ETA calculation with the ride service and also Uber Eats are extremely important. Therefore, we introduced aggregated sensor platform, which enables our deep learning model.
Yeah, so all this time we've been iterating, right? Our data scientists had come up with a deep learning model that takes in the raw sensor data and operates on that. It's simply an LSTM, a type of recurrent neural network good for processing time series data. And it takes in 3 different sensor streams, GPS and accelerometer, which I've already described, along with gyroscope, which we actually collected along with the accelerometer the whole time. And these sensor streams are then processed by the model to produce first a probability estimate of a label, crash versus no crash, along with a 100-dimension embedding. And then these 2 things are then fed into our original model as just additional features. We load the TensorFlow model within Flink and do the deep learning processing there, and then we still continue to consult the machine learning platform Michelangelo for the overall scoring, mostly for all the tooling it provides, like monitoring. And now we return to our original problem. How do we join these sensor streams? Well, a few things have changed. First, there's the considerable demand now from many teams at Uber. And along with that, there's been a lot of progress on the sensor side. First of all, we were now uploading GPS along with our other sensor streams. Because GPS is comparatively small, this makes sense. And together with that, we had solved a lot of timestamp alignment issues between GPS and accelerometer gyroscope, making especially raw data processing a lot easier. And so it was time for a sensor platform that does this aggregation once and for all for everybody and saves everybody the trouble, unlocking full trip raw data analysis, easy use of trip context data, which is so important, especially for our application, and also providing all sorts of data quality monitoring and guarantees. This was the first time we were looking into sensor data quality with such intensity. And so we produced a job consuming from trip aggregation. The trip aggregation job simply produces per trip sensor data, convenient for us. And then we were able to produce now just a single job in contrast to our modular topology. And the reason for this change, in part, the platform had simplified things for us immensely. After so much iteration, things were a lot more stable. And any breakdown into separate operators we could certainly do if we needed better monitorability of the Flink job.
Okay, lastly, we introduced the on-trip crash detection, which removes the dependency that we have to score trip as a whole on a post-trip basis, and we decide to continually score the trip while the trip is ongoing. However, the biggest challenge of on-trip crash detection is that it misses out some fundamental trip context. For example, whether or not the rider eventually reaches this destination, whether or not the rider or driver canceled the trip in the middle of the trip. So therefore, we propose a hybrid solution, which means during the trip, with the limited sensor data and business contact that we get from the trip, we continually to score during the trip. And once the trip ends, our post-trip scoring jobs start to score the same trip again to comprehensively understand whether or not this trip was involved in a car accident. And here is really lightweight topology of our architecture design, but due to our respect to time, we'll skip it for now and talk about our future development.
Sure. And so obviously the goal here, the thing we're most interested in of all, is being able to catch car accidents the moment they happen, right? And we've built a lot of infrastructure for processing things on the back end. And kind of the next steps for us are moving to an on-device heuristic or maybe even a light model, and then triggering early upload of the sensor data, something that wouldn't be feasible to do all the time. We can't break down and send up accelerometer data as often as we do GPS, right? But we can, under specialized circumstances, perform those early uploads and allow the back end to do the heavy lifting. That's all.
It's not about your pipeline, but about the technology that you have in Uber driver's car. Have you ever think of giving Uber drivers I don't know how it's called, like you can plug in a serial data port in most cars to get the data directly from cars? Is something you have thought about, or?
So, we've certainly done a whole lot of additional sensor collection relative to just phone sensor data. For example, the beacons that you see on the fronts of a lot of Uber cars also provide us with some much higher fidelity accelerometer and gyroscope data. It has the advantage of being firmly mounted on the car. There's no risk that a driver will be messing with that in the middle of an Uber trip. And so it's mostly sources like that. I think we've evaluated like onboard diagnostics, that sort of thing. And on the whole, there wasn't like a ton of additional value relative to the things we're already doing.
So you talked about Michelangelo and the time series RNN model, deep learning model that's trained. How often do you train that? Is it in real time, or do you train it once a day, or what's the
Which stream?
the time series data for you have the RNN model, right? The LSTMs, the deep learning model that you showed. And how often do you train that model? Is it based on the real-time data that's flowing through?
Sorry. We train it, it's basically just once. In general, we aggregated like a whole bunch of the sensor data, enough for us to train the model. It would be actually very intensive to retrain it very often.
Yeah.
Hello? I'm just going to, there we go. You mentioned that you were outputting some of the processed accelerometer data that other teams were sharing. So you had like some data coming into a Flink job, and then it was being outputted, and then some of other teams were using this data. Is that correct?
Yep.
What was the SLA that you were providing on that output data? Do you remember?
So the SLA of the aggregated trip data?
Yeah.
So that's actually provided to us. We're the beneficiaries of that job, but it's.
But you said you had some data going through your
The
Flink
stall
app,
feature.
and then that output was being shared by teams?
So there's a bit of confusion.
So we have two anomaly detection. One is the long stop detection. The other is crash detection. And originally, in the very beginning, it happens to be minutes after the trip end that we will produce the stop data. However, the on-trip anomaly detection is detecting long stop on-trip. So it needs to be real times and only a few seconds of delay. So this SLA doesn't really match up. That's why we separate our stop.
Thank you.
I think this will have to be the last question.
Do you assume the smartphone is fixed on some support on the car, or it can be taken in pockets?
Support on the car? You mean sensor collection or?
Yes. Do you assume that the Uber driver's smartphone is on some support, is fixed on the, or he can wear in his pockets?
Yeah, ideally we would like to have all the drivers mount their phones so that the data collection is more stable. However, it's currently not possible right now, but with drivers who have these Uber-provided beacon mounted on their car, it really helps us to calibrate different readings from different phones and different phone handling events that we could just get rid of the noise somewhat.
Just last question. Do you perform some pre-processing on the smartphone, or do all the computations on the server?
We tried to do virtually all computation on the back end as of right now, and it's only just now we're beginning to look at on-device computation.
Okay, thank you.
All right, thank you very much. I'm sure the speakers will be happy to take more questions outside.